Hi everyone. Welcome to Dave's Math channel. I'm your host David Tear. I made a video, really long video a couple days ago on it was called Mathematics, the Language of Science. It was an hour 20 minutes. That might have been a little too much for you guys. I don't know. So I just decided today I'd make a much shorter one. This is going to be a short and sweet one. It's entitled Euler's Prime Generating Formula, n squared minus n plus 41. I don't know how many of you guys are familiar with this formula. It's a formula that Euler came up with sometime in the 18th century for generating primes. There's no formula that's known that only generate, no simple formula anyway, that's known that only generates primes or always generates primes. But Euler's formula comes pretty close. It generates a prime for every integer n from 1 to 40, but then it fails for n equals 41. Pretty amazing. It's a quadratic formula. And here's another slide about it. Actually, they write n squared plus n plus 41. It doesn't really matter. It depends how you start n. If you start n at 0, then this formula works. It works up to n equals 39, which is equivalent to the one I showed you earlier. It's just that n is one less in this case. But it fails when n equals 40 here. That gives you 1681, which is 41 squared. I think it's pretty easy to see that when you plug in 40 for this formula, 41 for this formula, you're going to get 41 squared because, 41 squared minus 41 plus 41, the minus 41 plus 41 cancel, you're left with 41 squared, and the square of any integer is not a prime as long as that integer is greater than 1. So 41 squared in this case. But pretty remarkable that it works for every prime up to, for every value of n up to 41. 40 consecutive integers it works for. And this was this was the quadratic equation that generated the most consecutive primes, I think, until just maybe 20 years or so ago. I remember when I was still in graduate school. I guess it was more like 30, 40 years ago. I don't know. Somebody discovered a formula that I have to guess 43 or 44 consecutive primes. And the value n for that is much bigger than 0 to 40, and it's a much more complicated quadratic formula. This is a very simple one. So pretty remarkable that this works, I think. And I want to back up a little bit. This is based on something called an Ulam spiral. I think I talk about this in another video. I have another video on prime numbers, and I do mention the Ulam spiral. There was a famous mathematician, I guess he was a Hungarian mathematician, I think, Stanislaw Ulam, Romanian maybe. He was from Eastern Europe somewhere. But in the 1950s, one day he was at a lecture and he was bored. He'd had nothing better to do. He decided he's just gonna do a little diagram of integers going around in a spiral, a square spiral like this. And then he figured, well, why not? Just let's see where the primes lie on this thing. And much to his surprise, he found that there was a pattern. The primes seem to congregate along diagonals, like you can see here. I mean, it's not strict. There are places where you don't see primes, and I didn't make any bigger pictures. In my other video, I did. And there's a very a noticeable concentration of primes along spirals, and you don't have to start at 1. This picture we start at 1 in the middle. What happens if you start with 41 in the middle? Well, then you get another pretty fascinating picture. Actually, this one's even more fascinating because look at this diagonal line going up and to the right. These are actually all the primes in that formula. And it's pretty easy to prove that that's what you get. So you'll see 41. I don't know if you can see this clearly, but 41's in the middle of this diagonal. And then you got 43 off, looks like the top right. And then you got 47 in the bottom left. And then you keep going. You keep enlarging this diagonal. And each number you enlarge it with, the next, up to the next 40, is going to be another prime in this progression, n squared minus n plus 41. So that's kind of the pictorial representation of this quadratic formula. It's just the numbers on this diagonal, and the first 40 of them are all going to be prime, and then you're going to get some composite ones. So like I said, it's not strict, but the first 40 are. And here's a table. So this is a table of all 40 primes you get from this sequence. The last one shown in black here is what you get when you plug in n equals 40. This is n squared plus n plus 41, so 40 fails. That gives you 41 squared. But every other number on this table on the right column is a prime. Pretty amazing, and primes are kind of rare. I mean, if you just pick numbers at random up to 1681, most of them are going to be composite. The fact that this quadratic formula gives you all primes is pretty amazing, I think. And there is a mathematical reason for this. It's pretty complicated, though. I don't want to get into it. It involves some very advanced algebraic number theory, which is what I got my PhD in. You probably need to study algebraic number theory for about 2 or 3 years just to understand why this is the case. I do, but I'm not going to bore you with the details. Maybe in another video I'll do that. But for now, just notice this remarkable pattern of primes. And you might wonder what happens when you try bigger values of n. Well, I actually did this. This was a program I ran on my computer just a few minutes ago. So I tried plugging in every number, every value of n from 1 to 100. And this is n squared minus n plus 41, by the way. So you'll notice the p's stand for prime in the third column. There's 3 columns of this table. So the number in the leftmost column, and it's broken up into 4 parts. So just think of this as 4 partitions of this table. The first partition shows the values of n going from 1 to 25, then 26 to 51, so on, all the way up to 100. Second column shows you the value of n squared minus n plus 41 for that particular value of n. You see it starts with 41, then 43, 47, 53, so on. All these numbers are prime up to the 40th one, which is 1601. When you see like n equals 40, you'll see 1601, 41, 1681. That's the first one that fails, and I have a C next to it. The third column is either P or C. P standing for prime, C for standing for composite. So the first 40 of these numbers in the third, letters in the third column are all P, indicating that the number in the second column is prime. But then the third, the ones where it's composite, you have a C instead of a P. So the first C you see happens when n is 41. You might wonder how many other C's you get. Well, not that many. I mean, this formula still almost works, even for bigger values of n. It turns out that there's only 14. If you count all the composite numbers in this table, there's only 14 of them. First was n equals 41. Biggest, I think, is n equals 97. Turns out 98, 99, and 100 still give you primes. Most of the numbers, even after 41, are still prime. Pretty remarkable. So why, that's a deeper question. I haven't even really studied this question that well myself. I know why it's prime for every value of n up to 40. That's the algebraic number theory I was telling you about that I learned when I was in graduate school. But I really don't know why the density seems to still be high when n is even bigger than 41. I guess there's another reason for that I don't quite understand yet. But it seems to be true. So, like I said, primes are a little weird. They seem to be random, but at the same time, they seem to like certain quadratic sequences. So some weird stuff's going on with prime numbers. And I'm just going to say one more thing before I finish this video. There's another really fascinating thing in math called Ramanujan's constant. I don't know how many of you guys have heard of this thing, but there's a number called Ramanujan's constant. It's equal to e to the power pi times the square root of 163. It's a very big number. It's about, I think it has 18 digits, but then it's very, very close to an integer. The most fascinating thing about this number is that it's within about 1 part in a trillion of an integer. If you look at the digits after, so here, if you write out the integer part, you get 262, 537, 412, 640, 768, 743. It's actually closer to 744. It's almost exactly the integer ending in 744. And as a matter of fact, Martin Gardner once played an April Fool's joke where he claimed that this number was exactly an integer. This was back in, I think, 1975 when there weren't very good computers, and it was very, very difficult to prove that this wasn't an exact integer. I think if you tried to calculate on a computer, you probably would think it's an integer at that time. So that was a pretty convincing April Fool's joke, but it was an April Fool's joke. It's not an integer. but it's very, very close to an integer. And Ramanujan proved this. And it turns out that the fact that this is very close to an integer, I'm not going to go into this in this video, but the fact that this number, e to the pi times the square root of 163 is very close to an integer, is based on the same reason that the sequence n squared minus n plus 41 yields 40 consecutive primes. I know the reason for this too. I know the connection. It's a very difficult connection and involves the J function, this modular function called the J function. Probably take me an hour just to explain that. Pretty fascinating math. That could probably be another video too. But this is just another really interesting fact connected with this fact that, Euler's polynomial has 40 consecutive primes. So I think this is really fascinating math. Anyway, that's my video. Thank you for watching, and I'll see you next time.